Petrochemical facilities contain immense physical energy. Inside these miles of steel piping, extreme pressures and volatile fluids are constantly pushing against our boundaries, meaning a single mechanical failure can rapidly escalate into a disaster. The ultimate operational enemy engineers fight is a loss of primary containment, or LOPC. This is the precise moment hazardous material escapes its designated system and enters the environment. To prevent an LOPC, the industry relies on layer of protection analysis, known as LOPA. It is an exact, highly structured methodology used to design and calculate the strength of automated safety barriers. Safety in this industry relies on a mathematically defined architecture, built step by step to ensure that when a failure inevitably occurs, it stays within a tolerable, controlled limit. Trace a specific hazard scenario. Imagine a high-pressure gas separator where a crucial control valve suddenly fails shut, creating an immediate threat of massive overpressure. In Step 1, engineers use prior safety reviews, like HAZOP or what-if studies, to screen this exact scenario. They map out the physical chain of events to foresee the worst-case result of that valve failing before it ever actually happens. Step 2 assesses severity by strictly quantifying raw damage across 3 categories: human casualties, financial losses, and environmental spill volume. In Step 3, these values are plotted onto a corporate risk matrix, landing explicitly in a red critical zone. Step 4 introduces the Target Mitigated Event Likelihood, or TMEL. This severity category sets a hard mathematical ceiling on the maximum acceptable frequency for this disaster. By the end of Step 4, engineers have successfully translated a hypothetical physical explosion into a strictly defined ceiling of tolerable risk. Step 5 calculates the initiating event frequency. Engineers consult historical industry databases, like OREDA, to find exactly how often that specific trigger historically occurs. Step 6 takes that base frequency and multiplies it by situational modifiers, like a worker in the area or an ignition source. This calculation generates the unmitigated event frequency. In Step 7, the team identifies existing independent protection layers, like relief valves or standard alarms. They assign a probability of failure on demand, a reliable failure rate, to each of these layers. Step 8 brings these variables together. In this document's top formula, the intermediate event likelihood is calculated by multiplying the initiating frequency, the protection layer failure probability, and condition modifiers. For Step 9, the bottom formula shows all likelihoods are summed together. Steps 5 through 9 reveal the exact baseline risk of the facility. Engineers know the strength of existing defenses before new safety systems are designed. Step 10 compares our current risk against our target safety goal. This comparison reveals the exact mathematical gap that must be bridged by a new safety instrumented function. In Step 11, that mathematical gap dictates the required safety integrity level, or SIL, and the specific risk reduction factor needed to protect human life. The calculation must be repeated from the top, isolating only the barriers that prevent environmental spills, and repeated again for those protecting against financial ruin. In Step 12, the required risk reduction factors for safety, environmental, and financial impacts are compared side by side. Engineers must select the most conservative metric. By selecting the highest factor, here, safety, that single value dictates the final hardware design. This ensures the final safety system is engineered to handle the worst-case scenario, providing the necessary protection, whether life, land, or capital is on the line. The final result of this process is tangible: a completed safety loop, comprising a pressure sensor, a logic solver, and an emergency shutdown valve, is installed directly onto the gas separator, built to the exact specifications born from the LOPA calculations. This 12-step sequence allows process safety engineers to quantify abstract operational danger, establishing the verifiable performance requirements needed for every safety system on the site. LOPA functions as an invisible shield. It provides the calculated evidence that even when a high-pressure system falters, the plant's defenses are engineered to respond, protecting the workforce and the surrounding environment.